Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please hit the subscribe button right now. In the last couple of videos, I talked about pix-to-pix based CycleGAN. So there we used pairs of images that are related to each other. For example, a satellite image and its equivalent maps image. And we trained the GAN. So we can use the generator part of that GAN to create maps images just by using the satellite images. So in that example, you needed these paired images, one from domain A, the other one from domain B. What if you don't have the luxury of having those type of training images? For example, if you would like to convert a horse into a zebra, obviously digitally, how do you do that? Because you don't have like the same image of a horse that and the same exact looking image of a zebra. That's not possible. So this is where the unpaired image-to-image translation steps in. This is called CycleGAN, where you have a whole bunch of images in domain A and a whole bunch of images in domain B, but they're not related. They're not paired. But they represent, for example, domain A is all zebras or horses, and domain B is all zebras. I also experimented with a whole bunch of images of Srini, myself, and a whole bunch of images of zombie, and then see if I can convert myself into zombie. I only had like 25 images of each. They're definitely not enough for deep learning, but you can clearly see how I am a bit zombified a little bit here. Okay, so now let's get into understanding the concept of CycleGAN in this video. So I'll go through the original paper and highlight the key aspects, just like I did with the pix-to-pix paper. And in the next video, let's get into understanding the code and training a model. I love Monet paintings a lot, and also there is a data set out there that we can use. So let's actually take our regular photos and convert them into something that looks like Monet paintings. Okay, so that's the plan. So in this video, let's understand the background with a little bit quick look at some parts of the code, but the main part of coding would be in the next video. So I hope you'll stick around and then subscribe to this channel to get updated about any of these new videos. So let's jump in. Here is the paper that we're going to talk about. This is titled Unpaired Image-to-Image Translation using Cycle-Consistent Adversarial Networks. So this is basically CycleGANs. And there are a few examples, and in the next video we are going to use this example, Monet to photos, and these guys made all these data sets available so we can play with these. And of course, if you like horses and zebras, you can also do that, and a whole bunch of other examples. But first, a few key details from the original paper, starting with the abstract. So first of all, the reasoning for or the motivation for this paper is, we already looked at it. For many tasks, paired training data will not be available. So that's the key motivation there. And in this paper, they're talking about capturing special characteristics of one image collection, like whatever these Monet paintings are. What characteristics do these paintings have? And figuring out how these could be translated into image collection to the other domain. Of course, in the absence of any paired training example. So you still have two folders of A and B. A with a whole bunch of Monet paintings, B with a whole bunch of photos, and we are trying to convert, understand, or make this GAN understand the characteristics of Monet paintings, or what makes these Monet paintings, and then translate that into photos, and vice versa. So it's A to B and B to A. So that's the summary of this CycleGAN. And moving on, they exploit the property that translation should be cycle consistent. So there are a few terms that I want you to make sure that you understand. One of these terms, as part of CycleGAN, obviously it's in the name, is cycle consistency. What does that mean? Well, they clearly explain that here. When you translate something from English to French and then from French to English, then the statement that you get at the end should be identical to the statement that actually went in, right? So English to French and French to English, it should arrive back at the original sentence. So you take a Monet image, convert that to a photo, and take a photo and convert back to Monet image. So these two images should be consistent. So that's what cycle consistency is, and they explain that using a figure. So you can say there is a mapping function that takes you from Monet to your photos, and another mapping function from photos to Monet, like G and F. And think of, we'll get to this. We'll get to these mapping functions in a moment, but again, at a high level, hopefully that makes sense to you. Now moving on, implementation when it comes to network architecture. I'm just showing you only the highlights. Of course, the paper is, I definitely encourage you to read the entire paper, but just providing you a quick highlights from the paper here. So for network architecture, when it comes to the discriminator, I'm not sure they're talking about discriminator yet, but the key point I'd like to highlight here is they're using instance normalization, first of all. And for discriminator, they use exactly the 70 by 70 PatchGANs. Again, watch my videos, the 2 videos before this one, where I clearly explained what a PatchGAN is and what do we mean by 70 by 70 PatchGAN. But this discriminator is identical to the one that we have used as part of our pix-to-pix GAN, except instead of batch normalization, they're using instance normalization. That's the only difference here. Okay, so what's the difference? Again, this could be, you can go ahead and research what instance normalization is, but in summary, it standardizes values on each output feature map, on each of these output feature maps, rather than across features in a batch. That's the primary difference between instance normalization and batch normalization. Okay, and moving on, a few more training details. To reduce the model oscillation quite a bit, they update the discriminator using a history of generated images. So instead of, you know how you update the discriminator by taking a real image, right? You take one real image and then you take a fake image. And how do you get the fake image? You use the generator to generate a fake image, right? That goes into the discriminator. So instead of using that single image of, from fake image, they are actually training the discriminator using 50 previously created images, right? So they keep a buffer of these 50 previously created images, and they're using that to update the discriminator weights. That's another thing that's different from pix-to-pix. And of course, they are using very similar approach as pix-to-pix and other GANs, which is using Adam solver with a batch size of 1. So 1 image at a time, that's their batch size. And they're training at a learning rate of 0.302. And if I remember this is exactly same as pix-to-pix. And what else? Let's move on to understand the next aspect. And photo generation from paintings, and this also applies to, I think, a few other examples, but since I'm primarily interested in Monet 2 photos, so here they find it helpful to introduce extra loss and additional loss to encourage the mapping to preserve color. So what this basically means is there is another component. You know how you have cycle consistency? Now there is an identity mapping, so another term that they introduced. What does that mean? Well, your generator A, if it is supposed to take Monet images, or generator B, let's say, this is easy to explain, if it's supposed to take photos and convert them to Monet images or paintings, right? So it takes in photos and gives you Monet paintings. But instead of photos, what if you give it Monet painting? Well, it should not do anything to that painting, because this generator is trained to convert something that doesn't look like Monet painting into something that looks like Monet painting. But if you provide something that looks like Monet painting, it should give that exact same painting back. So this is what they call identity mapping when they get these real samples. So here is again a visual example right there. When you provide an input and without this identity loss, without training your model with the identity loss, you are losing that color information. It looks pretty realistic. It looks very similar, but you are losing that color. You see how you are losing that color right there. So with the identity mapping, that color is preserved, which is what we want for paintings, of course. So this is another term. Hopefully you understand what it does right now. And finally, let's look at the network architectures. And they provided the code in PyTorch. We'll be working with the keras code, but the network architecture itself is with 6 residual blocks. And first of all, they use residual blocks. We'll look at this in a second, but let's look at the network with 9 residual blocks. And this is how they put together. And what does that mean? C7S1, that basically means it's a 7 by 7 convolution. And S stands for strides, I believe, and stride equals to 1, and 64 is your 64 filters. So that's your first layer. And the next one is D128. D denotes a 3x3 convolution followed by instance normalization followed by ReLU activation. And of course, this 128 means the number of filters. So this is how they put together this model, and that's for your generator. And for discriminator, we already looked at it, right? So the discriminator is a 70x70 PatchGAN, and here is basically the discriminator architecture. So we'll again look at the code in a second, but just want to make sure you understand the pieces of this original publication that are highly relevant to what we are going to do later on in this video and also in the next one. So here is a few visually appealing images. I absolutely love this. You have an input of actual photos right there. These are literally actual photos, and they trained a bunch of algorithms. I mean, one that converts this into how this image would look like if Monet painted it, if Van Gogh painted it, and so on. So I love these. I absolutely love Van Gogh paintings also. If you ever happen to go to Amsterdam, this is a great place to stop by the way, the Van Gogh Museum. Okay, moving on, let's look at the discriminator architecture and the generator architecture and end right there. So first of all, the model has 2 generators and 2 discriminators. Okay. And we'll get to why 2 generators are, in a second, basically. But discriminator and why 2 discriminators also. But both discriminators, they have exactly the same structure. 70x70 PatchGAN. We looked at this in a couple of videos ago. And except here we use instance normalization. So as you can see, here you're still using the random normal initialized weight initialization method. And you have your conv and leaky ReLU conv, and instead of batch normalization, we replaced it with instance normalization. That is pretty much it. Okay, and we have our same leaky ReLU with our slope of 0.2 and so on. So this is our discriminator. Not much to explain, and as you probably know, like in any GAN, discriminator is trained directly on the generated and real images. Except we learned that it's not just using one fake image. It's actually using a pool of 50 fake images, right? I mean, that's exactly what we saw earlier as part of this paper. Okay, now let's move on to generator, because this is the more complicated one in this model. So there are 2 generators. Why? Generator A, it generates images for the first domain. For example, our first domain is Monet and the second domain is actual photo. So generator A generates Monet paintings. Generator B generates photos, because we have 2 things, right? We are trying to generate the paintings and also photos here. So this is these are 2 generators that we have. Okay, moving on. Input to generators comes from the other domain, obviously. So generator A is generating Monet painting, so the input is going to be a photo. Generator B is generating photos, so the input is going to be Monet painting. Think of these as even horses and zebras. So you supply a horse, you get a zebra. To get a horse as your generated image, you supply a zebra. So it's the other way around, right? And each generator has a corresponding discriminator, because we have 2 generators, generator A generating Monet, generator B generating photos. We need 2 discriminators to discriminate these 2. So you can think of this as, okay, you supply a Monet painting to your discriminator. It is trained to it is going to be trained to classify this as real or fake. Or your photos are going into generator A. What happens if your photo goes into generator A? You get a Monet painting, because that's what it's going to generate, and that goes into discriminator A, because this discriminator is only going to take Monet paintings as input and then give us real or fake. Exactly opposite to discriminator B, which works on the photos domain. Okay, now let's understand this a bit more. We looked at cycle consistency, right? So what does cycle consistency means? The generator models are trained to reproduce the original source images. So this is what cycle consistency is. So use a generated image as the input to corresponding generator. I think this one explains it much better. So you put a photo as an input to generator A. What do you get? A Monet painting. And now you take this Monet painting as an input to your generator B, and then you should get your original photo back. And now you compare this photo against this photo, and there you go. That's your loss. That's your cycle consistency loss. Exactly opposite to with your generator B, where you get Monet painting in, and then this generates a photo which goes in as input to your generator A, which eventually generates your Monet paintings, which is nothing but your input, and you compare this output to your input, and this is your cycle consistency loss for Monet painting for your other. So think of this as a forward cycle consistency. Think of this as a backward cycle consistency. Yeah, a forward where you're going from photo to photo, a backward when you're going from Monet to Monet. So there are, in fact, two losses here, not just one, within the cycle consistency. I'll put all of these together in the next slide, so it at least summarizes at the next level. But looking at the identity mapping, so we also looked at identity mapping. So when an image from the other domain is provided, it is expected to generate the same image, because generator A is expecting a photo to be an input, so it can generate a Monet painting. But if you provide this with a Monet painting, it should not do anything. It should just give that back as is without doing anything. Same with generator B when it comes to photos. So this is what identity mapping is. So basically, this is another loss where you provide generator A with Monet painting, and then look at the output, and then compare this output against this. What do I mean by compare? By the way, when I say use this as a loss, you have an X, which is your Monet painting, and you have a Y, which is your Monet painting that your generator generated. So you compare these two by using L1 loss or L2 loss. So in other words, by using mean absolute error or mean squared error between these two images. That's what we mean by using these as losses. Okay, how many losses do we have? That's a quick quiz for you. We saw our actual discriminator loss, right? I mean, the actual GAN loss. And then we have two losses here under cycle consistency, forward and backward. And then you have identity mapping. So there are total 4 loss functions that we're trying to minimize as part of our training. So now let's go down to generator architecture. How do we put this generator together? Well, they already mentioned that they're going to use ResNet blocks as part of the generator. So first of all, you probably know what a ResNet is, or a residual block is. If not, again, I encourage watching my earlier videos when we looked at a residual block as part of unit, when we were building unit. That was a few months ago. But the same concept repeats, right? I mean, we are just using the core concept of residual block, which is basically you have an input, an input, and that inputs, the next thing it goes through is a convolution layer, batch normalization, activation. Except, again, in this case, they are using instance normalization and not batch normalization. Okay, so con 2D, normalization, activation, and then con, and then normalization. The output that you get from this operation is going to be concatenated with the input. This is exactly what a residual is. So that's what finally you get here. Concatenate your G, your output right there, with your input layer. So this is your residual block. Now that you understand residual block, let's look at the actual network. So we saw this screenshot earlier. You either have 6 or 9 residual blocks. I only tested the 9 residual blocks one, where the model architecture is 7 by 7 convolution with a stride of 1, 64 layers, 64 filters, and then 128 filters, and so on. And here you have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9 residual blocks. The R stands for this residual blocks. 9 of them, one after the other. And then comes your upscaling, or upsampling, if you want to call that, or con 2D transpose operations right there, and finally this. So if you put everything together, this is how the code looks like. So you're defining your generator, you have your input image right there, and what comes first? A con 2D 7 by 7 with 64 filters. That's it. Yeah, that's what that is. With a stride of 1. So if I think the default stride is 1, so if we don't define it explicitly, then it's going to use 1 by 1. So if you want, you can define that explicitly here. This followed by instance normalization, followed by activation. And then comes our D128. D128 is con, 128 filters, 3 by 3 and strides, and then instance activation. D256 is exactly same, except here you have 256. And then comes our residual network blocks. 256, 256, 256, 256, 9 times. So here there is a for loop that adds these 9 times. 256 and adds the residual block that is coming from here. And then comes your U128, con 2D transpose 128, and then 64, and finally C7S1, which is basically your convolution, 7 by 7, stride equals to 1, and 3 channels right there, right? I mean, RGB channels that we would like to export right here. So this is, I mean, once you understand this paper, I think it's pretty easy for you to put these things together. So let's go ahead and now let's see how we are going to train our generator. So now we have our generators. How are we going to train? So obviously, like any GAN, it's trained via the combined model, where you keep the discriminator constant and then you only train the generator, right? So this is how we train our generator in a normal GAN anyway, except in this case, we have 4 different losses that we have already looked at. What are these 4 losses? We have adversarial loss, like this is our just our GAN loss, and this is our mean squared error, L2 loss, and it's basically minimize the loss predicted by the discriminator for these generated images. So this is our GAN part. Yeah, nothing, this should not be surprising. And the identity loss is also, I mean, we just discussed about it. Identity loss, they suggested that to be L1 loss, which is nothing but mean absolute error. Yeah, L2 loss is mean squared error. So here, again, we already know what identity loss is. Your output image and input image should be the same for the second GAN. So that's what we are trying to compare, and we are minimizing the mean absolute error. And cycle loss forward, remember, Monet to Monet, and then backward is Monet to, I should have said Monet to Monet, sorry, and photo to photo, right, in the example we saw. This is also a mean absolute error, and backward is also a mean absolute error. So in our loss, we have 1 adversarial loss and 3 of these losses that are all L1s. How do you train that? How do you put them together? Well, we have put our generator and discriminator together in a couple of our videos already, where we talked about GAN and pix-to-pix conditional GANs and pix-to-pix and so on. You define the combined model or composite model, where you put your generator to be trainable, but then discriminator to be non-trainable. But here we have 2 generators, 2 discriminators. So what shall we do? Well, first of all, let's just look at our generator. Think of this as a generator for Monet paintings. We are trying to train a generator for Monet paintings. So the generator 1 is trainable, yes. This is what we want to train. But then we don't want anything else to be trained at that time. We want all the others to be constant, which means we have to make our discriminator to be non-trainable. We want our other generator to be non-trainable. The same function, I'm going to call this again, while I'm training the photo generator. In that case, this is my photo generator, the generator that generates the photos, and this will be trainable, and the one that generates the Monet paintings will be non-trainable. Okay, so just think about this. And then we have 4 losses. One is adversarial loss. We have done this many times in the past, right? I mean, you have your input, and then you have your generator model on your input, which gives you the output of the generator, which is nothing but the input to your discriminator, right? So the output of generator is a fake image that goes into your discriminator, and that's what your output is. And you compare this output with your input, and then you're basically minimizing whatever that function that you use as a loss function. So in this example, your adversarial loss is going to be a mean squared error, right? I mean L2 loss, and all the other ones are L1 losses. So here you see if we have 4 losses: mean squared error, mean absolute error, and absolute error. So these 3 are for these 3. Okay, we are going to define that in a second. So first, adversarial loss, then comes identity loss here. So identity loss is, again, we already talked about this. So when you have a generator model here, and you have an input that actually comes from a different domain than what it is expecting, then I mean, again, just to repeat this, the generator that is supposed to generate Monet paintings is expecting photos as input. But if you supply Monet painting as an input, it should generate Monet. So that's what identity is. So that's exactly what this is doing here. And you have your output there, and then you have your cycle loss forward, and then you have cycle loss backward. Yeah, so these are the 2 losses. So how many outputs do you have? Output 1 right there, output 2 right here, output 3, and output 4, right? So these are the 4 outputs we have to compare against inputs. So that's what we are trying to do here. My model has input generator and input ID right there, and it has 4 outputs, and corresponding to these 4, we have these 4 losses right there that we are trying to minimize. And the Adam solver with a beta equals to 0.1 is exactly what they suggested in the paper. And for these 4 losses, we want to weight these losses. Again, this is suggested in the paper. We want to weight them as importance of 1 for your L2 loss. And if I remember this correctly, for pix to pix, this would be, we had 2 losses and we weighted them as 1 to 100. So here we're weighting them as 1 to 5 to 10 to 10. So these two, cycle loss forward and backward, they get equal weightage. And our identity loss has half the weightage as our cycle loss. And then your adversarial loss is 1/10 of your cycle loss forward and backward. So that's what this is. So let's end here for now, and in the next video let's pick it up from here and start writing or start going through the code, and let's convert some Monet to photos and photos to Monet. And while I'm there, I'll see if I can just also walk you through Srini to Zombie and Zombie to Srini. So thank you guys, and please stay tuned for the next video, and again please go ahead and subscribe to this channel. Thank you.